Oh, hello everybody. This is the this is the last lecture about the rapidly varied flow. Sorry, just yeah, slowly varied flow. And you remember that we were talking about the flow change from I mean in the channel if the flow is experiencing a hump. And today I will continue almost the same concept but with different perspective. In this case, you are going to learn that what happens if the channel width changes. I mean, if you have a kind of narrowing, I mean, contraction in the channel width over the flow. If the water experiences it during the flow, what is going to happen? We are going to discuss this topic, and it is an interesting topic. It is the same principles applies. So that's why I am going to start introducing the topic with you to you by focusing on the specific energy graph, and then we will go into details by solving one problem. Okay, let's have a look at that. What's going on here? And okay, this is an intersection wheel, horizontal wheel actually. But if we look at from the top, you will see that the channel is going to get narrower, okay, in terms of width. In terms of width, let me show you this example. You will see that what I mean. Okay, so channel is this is top wheel. Channel is coming with a kind of width, and then it turns into a narrow channel. Okay, so there's a contraction here, and today we are going to talk about what happens if you experience such a kind of contraction in the channel. So the specific energy diagram is given on the right in such cases, and please note that and I want you to remember that what is small q, it means specific flow rate. It means that the flow rate is divided by q. It means divided by width, and if q gets larger, it means that width is getting narrower. So in such a case, I mean, if the flow is not getting narrow from point 1 to 2, it means that the section, I mean, the cross section on L is smaller width than point 1. So in this case, you are going to have a larger specific flow rate. Okay, I mean Q2 is going to be larger than Q1 because you have narrow bottom width here. It is wide bottom. This is wider here, and the value of Q2 is going to be larger than Q1. So in this case, you are going to have different Q values. It means that you are going to have different specific energy values as given on the figure on the bottom. Okay, so for example, let's say that this Q1 is our original flow rate, unit flow rate. Okay, so this is our unit flow rate. And if you have a kind of a narrower width, then you are going to have a specific energy, which is like this one. And if you keep having a much narrower flow rates, width, then you are going to have other specific energies which are following this trend. Okay. And in our case, what is going to happen? Have a look at that. We are going to have, for example, from point 1, if it is subcritical flow, and just focus on where, oops, just please focus on where I am addressing with my cursor. This is the original case with Q1. Okay, this is the original case with Q1. And if the flow experiences a contraction, then you will have Q2 larger than Q1, and this is the new specific energy. And of course, the height is going to be lower. So if you have a narrow channel for subcritical flow, then you are going to experience that the flow rate is going to get, I mean, the depth of the flow is going to reduce. Okay, so Y2 will be lower than Y1. And when you reach the critical flow, okay, the critical depth on the channel, it is exactly here. That flow, that energy curve cannot carry more than this height. So if you keep increasing the narrowness, I mean, if you keep actually decrease the width, then you will exit this point, and what is going to happen? Have a look at that. What is going to happen? So this is going to go up, and of course the original height will go up too. Okay, so there will be rises in both sides, on the right and left sides. I think it will be easy if I explain you in these graphs. Okay, actually these are the similar graphs you are familiar with in the earlier lecture. So please have a look at that. What we have. This is the point. Okay, let's focus on first subcritical, then we will continue with supercritical. And this is the point of no contraction. Okay, so that's why B2 over B1 is equal to 1 here. Okay, it means that the flow is just continuous as it is. And just after this point, if you keep increasing, sorry, if you keep decreasing the width of the channel, then what you are going to have, you are going to have a decrease in the length on the contraction part. However, the width of the channel on the original part, I mean upstream flow, is going to stay almost, is going to remain almost the same. Okay, when you reach the critical depth, okay, when you reach critical depth, it is exactly the point which I mentioned here. Okay, when you reach the critical depth, then you will have a kind of increase on the right side, I mean downstream, but at the same time you are going to have also increase in the upstream flow. So still the channel will carry the flow, but on both sides there will be a kind of rising up in terms of water depth. Okay, so these are the things you can easily calculate. Anyway, I am going to solve one problem. I think you will understand in a better way. If the flow is supercritical, again, this is the point, there is no contraction, and when you start having a kind of contraction, or I mean like narrowing in the downstream, then you will see that this is the original flow. It almost remains as constant until you are reaching, okay, until you are reaching the critical flow point, but the depth on the right side is going to be high or higher. So if I don't give you any information about contraction, and if I provide you a kind of, for example, water profile, and if the flow on the left side is I mean, if the water depth on the right side, I mean, downstream is higher than upstream flow, you will know that it's supercritical. Okay, and when you reach the critical flow, the depth on the upstream will start decreasing due to a higher velocity, but the depth on the downstream will goes up. Okay, it will goes up. It will experience a rising. These are the cases for subcritical and supercritical. Those figures exactly follows the principles of specific energy, and those figures are extracted from these specific energy curves and equations. Okay, this is the theoretical part, and now I am going to solve you one problem. Then, as I told you, that lecture will be over. It's going to be a little bit short session today, just 20 minutes or something. So, do you have any questions in terms of theory? Did you get it? What I am talking about? Any questions, please? So, are you saying something, Oscar? No? No one is saying anything? Great, it seems that it's clear. Okay, let's solve one problem. Maybe you will understand better. And if any question, I mean, appears in your mind, please just do not hesitate and ask me immediately. I will be happy to explain it. Okay, let's have a look at this question. Okay, again, this is the top view, and this is the cross-section, horizontal view. Okay, so you'll see that water is flowing from left to right. So point 1 is upstream, point 2 is downstream, and the width of the channel is here 3.5 meters, and it is ending up 2.5 meters, and there's a contraction here. Okay, and the water height is 2 meters, as given 2 meters, but at this stage we don't know it is subcritical or supercritical flow, but I am telling you that it's going to be subcritical flow. That's why I provided this figure too. So you will see that after checking the Freud number and the critical depth on the first place, I mean the first section, you will see that it's going to be subcritical flow. If it is subcritical flow, then there will be, I mean, the second flow, I mean the flow in downstream will be again subcritical flow, but the depth of the water will be lower than the original depth on the upstream. So let's calculate. Okay, the first thing is first, we are going to calculate the Freud number at 0.1. And in order to find the Freud number at 0.1, we should first calculate the velocity. And the flow rate is given as 15 cubic meter per second. And we are dividing this velocity, flow rate into the area. And the area is given as 3.5 times 2 meters. 2 meters is the depth. And then you are going to end up with 2.14 meter per second as the velocity at 0.1. And it is easy to calculate the Freud number. The equation is given here, okay? And when we calculate the Freud number, you will see that it is smaller than 1. It is 0.48. So this value is smaller than 1. It means that the flow is subcritical. So, so exactly this figure is correct. So if this subcritical flow, it will continue as subcritical on the right side, I mean on the downstream flow. But the thing is that you should remember the depth of the water on the right side should be always lower than the depth of the flow on the upstream. So you will get Y2 value as smaller than 2 meter. Okay, this is what you should note. And when you complete your calculations, you should be sure that it is smaller than 2 point, then your calculation is correct because it is subcritical flow. And let's calculate the energy, specific energy at 0.1. It is easy. The specific energy equation is this one. And if you put everything together into the equation, you will end up with 2.23 meters, okay, as the energy, specific energy of the system at 0.1. And here, the term, okay, these points in those graphs, okay, these points exactly the where you are going to have critical flow on the downstream, it's called choking point, okay? If you are having a kind of flow regime, which is not able to tolerate the critical flow, it means that more than critical flow, and you can say that there is a choking. Choking is occurring here. It is like a kind of choking. If choking occurs, you should calculate the upstream flow depth again because the water is going to bounce back, okay? And everything will be different. Even the original height as given here, okay? The original height as given here will not be the original, not resulting height. It means that if there's choking because of the critical, so think in that way, the flow is going to, if the flow depth is reaching critical depth on the upstream flow, downstream flow, there will be choking. Okay, choking means that the channel at the contraction part cannot carry that amount of water. That will be rising up a little bit. Because of this rising up, the water will bounce back, and the water depth on the upstream will be also higher than this one. So you will know that the original, I mean the resulting depth on Y1 will be also different than 2. It will be higher than 2. Okay, so let's check for choking. In contraction problems, you should make a kind of choking check. So in order to check it out, you should check that if E1 is equal to E min. Okay, if it is, then you will say that, or if it is larger than this one, then you will say that, okay, there's choking occurs. Okay, so let's check it out. The Y critical is equal to 2/3 minimum specific energy, and this is our specific energy. So Y critical is supposed to be 1.49 meters. Okay, so for 1.49 meters, okay, we are going to calculate the critical depth, and the critical depth is here. 1.49 meters, and we are going to calculate the B value for this critical depth. And if you calculate the B value, the maximum maximum contraction to have a critical depth on the downstream is 2.63 meters. You see that we have 2.5 meters here, 2.5 meters here. It means that it is narrower than the critical depth. It means that choking is occurring. So this, I mean, if the width on the right side is larger than 2.63, it is fine. Okay, there is no need to calculate the ending depth in both in the origin. I mean, upstream flow, it's going to be 2. But if it is narrower than 2.63, as it is given in the question, it is 2.5. You will know that the water is going to bounce back, and you cannot retain the height, original height on the upstream tool. So let's check out what's going on here. And we know that choking occurs, and the B value of the downstream is not good enough to carry this water without having choking. Then let's calculate. Let's run the calculations in the next stage. You will see that, okay, let's calculate the depth on the right side. And this is the Q2 value on the right side. It is 15 over 2.5. And it is 6 square meter over GS. And look at that, this is not cubic meter, this is square meter. It is Q value. I explained it several times in the earlier parts. And then the critical depth on the right side is supposed to be 1.54 meters, okay? So with this volume, we know that the flow should be at critical depth, because if choking occurs, the channel on the downstream cannot carry more than, I mean, higher any depth, lower or higher depth. Sorry guys, the channel cannot carry any value than more than this one. So you should calculate the critical depth as, and then you can easily find it that it is 1.54 meters. Okay, so this is our new value. This is our new value for the downstream flow, and you are going to refer it. And I suggest you again, the calculations are not over, because we know that there is choking. If there is choking, the original height on the upstream flow will be different, because there is bouncing back, okay, because of the choking. So let's calculate the possible energy change on the system. So if you calculate, and if you calculate the new energy value by just multiplying this value with 1.5, then you are going to see that the energy, the specific energy, is supposed to be 2.31 meters. But in the original flow, let's go up. I will show you. In the original flow, the specific energy was 2.23. Okay, the specific energy was 2.23, but it's supposed to be 2.31 after the choking. It means that there is a kind of increase in the specific energy even in the upstream flow. So you are going to use this new value, okay, to calculate the possible the possible rising, okay, in the equation, the energy equation. Then you are going to calculate the new value. So you will see that the new value for the upstream flow is going to be 2.10 meters. Okay, so this 2.1 meters means that, okay, this flow is reaching more than the capacity of the channel to carry out the critical depth. That's why choking is occurring. So you are having a kind of different critical value for the given flow, and the water is bouncing back. For the new energy value, you should calculate the upstream flow height, and then you may see that there's a kind of bouncing back on the upstream flow, okay, when you reach the contraction, and it is going to be 2.1 meter. You are going to end up with 2.1 meter in the upstream flow. In the downstream flow, the depth is the critical flow with this condition. It is actually given here 1.54 meters. Okay, so I'm going to upload this problem, these slides on Moodle. I strongly suggest you to focus on it, think about it, and try to solve it by yourself. And this is one of the most complicated problems you can get in this section. Okay, and I will not solve more problems on this topic. And next time I will continue with rapidly changing flow. And now I am ending the gradually changing flow conditions for open channel. And after the spring break, we will continue with the rapidly changing flows, and we will learn 2 more topics. Then hydraulic will be over. Then we will start with hydrology. Then you will learn hydraulic jumps and other stuff. I think it's going to keep us busy for 1 more week after the spring break. Then the rest of the lecture will be given to hydrology part. Okay, it seems that I am done. And guys, I will also upload your second problem solving assignment on Moodle, possibly in this week. I will inform you by sending an email. Just be ready for it.
Professor, regarding this assignment, can you please set the deadline after the fall break?
Why?
Oh, sorry, I mean after the spring break.
Why?
We have a lot of homework if it's possible.
I am not pretty sure. I have to think about it. Takmina. It is possible, but extending it because I have to give you four problem solving assignment. I already gave one, and you are going to get the second one before the fall break. Actually, I am a little bit late. I should give it in the earlier week, but I didn't give it because you had a midterm. Because of those delays in the early parts of the lecture, we are behind the schedule. Okay, I am going to think about it, but most probably I will give you the assignments in this week until Sunday, and I will allow you to complete it for 1 week during the spring break. So what I can do, I think I can prepare a kind of question, not taking too much time to solve it. Maybe you should use an Excel and solve it, make a kind of simulation. This is what I am planning. Actually, I am going to give you a kind of assignment to make a kind of simulations like the graphs on this figure, okay? I want you to make a kind of simulation by numbers to obtain those graphs in Excel. I will give you the guidelines. It is not going to be very difficult, but I'm not pretty sure that if I can extend it for 2 weeks, okay? I don't promise. Well, I need time. There are not too much time left for this course, and you should still complete 3 problem solving assignments. If I give you extra 1 more week, then most probably you are going to have other assignments for shorter terms, times like 2 or 3 days. It is not reasonable. It will be more difficult for you. So I am sorry, I may not say yes for this request. Okay, any other things, please? No?
No questions?
Okay, but again, don't be upset. I will do my best. Okay, I will do my best. If I can do that, let me check again the timing. If it is possible, I will give you an extension or an extended time, more than 1 week. But I have already made a kind of calculation for the remaining times. It seems like not quite reasonable for our case. Okay, guys, it is done for today. See you on next time. Okay, bye-bye.
Thank you. Goodbye.
Goodbye.
Goodbye.